In this video, I will go over the homework that follows the lecture on the direct comparison test, which is the first of the two comparison tests that we are going to cover. And as always, I hope that you watched the lecture first. And now let's go ahead and take a look at the homework. And the first question here is, which of the following series should be used to determine the divergence of this series? So the idea is that we take a given series and we compare it with another series, and if it's greater than a divergent one, then it diverges, and if it's smaller than a convergent one, then it converges. So we have to strategically pick that other series to make the comparison valid. And in this case, it looks like that we're going to start with the denominator, and it's clearly, well, if we just preserve the denominator at first and then try to figure out what to do with the numerator. So this series diverges because it's a harmonic series, and now in order for the comparison to be valid, we have to make this inequality and check if it's true, and it seems like to be true because this radical expression is always greater than 1, and therefore this series diverges as well by the comparison test, by the direct comparison test. So to answer this question, we would pick this one, but the full test involves a little bit more than just picking another series. So let's take a look at another problem. I'm just looking at this solution, and it's that they're making it very complicated here. And the reason they're making it right, so this diverges even by the divergence test. So we would never get even to the point where we'd have to consider a comparison test here, because it diverges by the divergence test. So that's why these two lines kind of make no sense whatsoever. So yeah, let's go to the next question. All right, so the next question is, it's similar to the previous one, and here's what we're going to do. We're going to conclude that this series is smaller than this series because it has a larger denominator, but this series is actually a geometric series with a common ratio of 2/5, which makes it convergent. So this series converges by the comparison test, and we compared it with a geometric series. So this will be the answer. This series is smaller than this series because it has a larger denominator, and this series is P series with P equals 3, and since 3 is greater than 1, this series converges. And this also converges because it is smaller than a convergent series. Here we have a series and we are going to compare this series with this series. And how do they compare? Well, the original series is less than this series. Why? Because we have subtracted multiple terms from the numerator, and we have added multiple terms in the denominator, positive terms. So when you take away from the numerator and add to the denominator, your series or the expression becomes smaller. Now, once we establish this inequality, the next thing for us to notice is that we have this, and 1/2 can be factored outside, and we have n squared in the denominator, so this is P series. P is equal to 2, which is greater than 1, and therefore the series converges. That means the original series also converges by the comparison test. It is smaller than another convergent series. So the answer is the series converges. And this was the last problem on the homework. If you have any questions, feel free to reach out.